Halo, selamat pagi. Ohayou gozaimasu. Suara saya terdengar ya?
Terdengar, Pak.
Oke, baik. Saya mulai saja ya. Baik, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi semuanya. Good morning everyone. Semoga sudah sarapan semua ya. Atau baru bangun tidur ini? Oke, sorry for this inconvenience ya. Today is the substitution lectures because yesterday I had to go to Malang ya for a workshop. So I become the speaker of the workshop. But next week, hopefully, we can have the normal lecture on Thursday and Friday. So Mahesa, is it clear?
Yes, sir.
The fluid masonry?
No, the machinery can't be rescheduled, sir.
Okay, hopefully it's not on Friday morning, yeah? So let me know, yeah?
Yes, sir.
Okay, so I will start today for the next module of combustion calculation with a video. Yeah, this is maybe the same video in the first meeting, yeah? Wait a moment.
Today's boilers, as they have been since their origin, involve.
Can you hear the video sound?
Yes, sir.
Complex production
Yeah?
and manipulation of steam.
Bisa kedengaran ya suaranya ya? Ini saya pause ini.
Dengar, Pak.
Bisa ya?
Bisa, Pak.
Okay. Okay, I repeat.
Today's boilers, as they have been since their origin, involve the complex production and manipulation of steam.
The force multiplier blows air into the system. A portion is routed to the pulverizers, which crush coal into a fine dust. before pushing the mixture up through feeder tubes. The other portion passes through an air preheater, which transfers heat from the exhaust gases to the incoming air, raising the air temperature, reducing moisture, and producing a cleaner burn. The hot forced air and coal dust converge in the wind box, where the mixture is blown out through burners and ignited inside the firebox, transferring radiant heat to the water-filled tubes. The hot gases flow upward, heating the rest of the system through convection, before passing through the air preheater and ultimately flow to the scrubber, where pollutants are removed.
Okay, so we see this video. So the video figure out the basic operation system, the running of boiler. Start from the combustion process here inside the furnace, to burn the fuel and heating the tubes. So we can see this is a kind of animation. This is not a real boiler, but almost similar with the real boiler. So many tubes, numerous tubes inside the furnace, contains of water inside. And then the furnace make a combustion process, to burn or to heat the tubes, the rising tubes. And then the flue gas goes to the stack, or maybe this pipe, the port of the exhaust gas. And then there's many systems that we will discuss later, from the firing system, the feed water system, the exhaust gas, So let's continue.
The hot gases flow upward, heating the rest of the system through convection, before passing through the air preheater and ultimately flow to the scrubber.
So as I mentioned maybe in the former meetings, so the exhaust gas or the flue gas is not only to heating up the rising tubes, but the rest of energy can also be utilized to heat the superheater, the economizer, and also the supply air preheating. So the preheater is very important for the supply of the air, for the combustion process in the boiler, because this is external combustion engine, different with the internal combustion engine. So the exhaust gas, before discharge it to the atmosphere, sometimes needed to flow it to the scrubber, to reduce the emission.
Where pollutants are removed. Liquid water is pumped into the system at the economizer. Gradually, it's heated to base temperature before gathering at the steam drum, the system's main distribution hub for circulating water and steam through the boiler. Liquid water flows through large handcummers and into the base of the firebox. A network of 2-inch tubes line the firebox walls, and burners force feed a continuous supply of combustible fuel into the ultra-hot firebox. Eventually, the insides of the firebox burn so hot that its surrounding steel walls would melt if not for the tube-lined walls of liquid water. At the point in the cycle when the liquid water turns to steam, the steam separates and collects at the top of the steam drum. Because this saturated steam still contains small amounts of liquid water that would cause corrosive damage to the turbine, the saturated steam is routed back into the firebox and through superheats to burn off all but the smallest traces of liquid water. This dry, superheated steam then exits the boiler, passing through a steam locker and ultimately providing power to the spinning turbine, which generates electricity. Finally, exhaust steam, now at a lower temperature and pressure, is sent back to the boiler through a dedicated reheat stage. This reusable steam is brought back up to operating temperature before returning to the turbine, providing additional power through a secondary stage.
Okay, so today we will not discuss about the steam circulation or maybe the air preheating, the another system, but we will focus on the combustion. Yeah. So from this video, maybe you have seen the first step of the boiler operation. Yeah. So you have a combustion inside the furnace, and you have also the rising tubes contains of water. Yeah. And then the flue gas or the exhaust gas should be discharged to the environment. Yeah. But before discharging to the environment, then you can use it, yeah, as an energy to heat the steam, yeah, the saturated steam. You heard about the explanation. The steam from the rising tubes goes to the steam drum, but the condition is still in the saturated condition, and it is not allowed to use it desaturated for the rotating turbine. Yeah, so you have to superheat first. Yeah, in the superheater you have the dry or gas vapor form. Yeah, and then you have also the economizer, the air preheating systems. Yeah, and also later we will also talk about the exhaust gas and also the feeding, yeah, the steam management, yeah, the condensate management also. Yeah. So about the combustion calculation here, yeah, as I mentioned maybe yesterday or on Thursday, the main important value from the fuel is the calorific value, yeah, because you burn a certain amount of fuel to have a certain energy, yeah, to give a certain energy for heating. Yeah? So you convert from the bound energy in the fuel, convert it into the heat, yeah, and then convert it into the steam. Then the steam will goes to the turbine. Yeah, so actually you have many process of energy conversion. Yeah, so that's why it is important for the engineer or maybe the design of the boiler, yeah, to know the characteristic of the fuel, the firing system, the type of or the method of combustion process. Yeah, this is very important. So today I will start with the basic of fuel combustion. Yeah, the calculation or the analysis of the fuel combustion. Okay, so I stop this video and then I will share the module of combustion calculation. Yeah. So I hope you have downloaded the modules, yeah, in the classroom. Okay, can you see the slides now?
Yes, sir.
Okay. So the combustion calculation is the fourth module. We will talk about the stoichiometric. Yeah, this is one of study for the basic knowledge, yeah, the basic theory for the combustion calculation. So stoichiometric you have studied, I believe, in the high school, maybe in the senior high school for the chemistry, yeah, in the chemistry lecture, yeah, class, yeah, in the chemistry class. Or maybe during the first or second semester, yeah, you will study about the chemistry. Yeah. So this is a basic study for the combustion calculation because the stoichiometric involves the basic of how to know what are the components of the fuels, yeah, for the reaction of the chemical bounded in the fuel, yeah, the chemical reactions. And then also the non-stoichiometric, the practical practice aspects the firing system, the basic, and later we will study more about the firing system in the next module, and also the exhaust gas specific heat. Yeah, and then we will end our lecture today for the example. Yeah, the example of problems for combustion calculation. So for the stoichiometric or the elementary analysis of the fuel, you have to know first the components bounded in the fuel. Yeah. So as I explained on Thursday, so you can use any kind of material as fuel if the material has the main component of the carbon. Yeah, so the carbon is the very most required of fuel. Yeah, and the other components is a small amount. Yeah, small percentage in fuel, but totally you have 100% components. Yeah, so we have carbon, hydrogen, sulfur, oxygen, nitrogen, ash, and water. Yeah, on Thursday I explained to you about this component in the hard fuel, liquid fuels, and also the gas fuel. Yeah. So mostly during the combustion process, yeah, maybe you have also studied in the internal combustion engine, or maybe the lecture of diesel engine. Yeah, you have studied about the combustion calculation for the diesel engine, or the reaction between the fuel and the air, yeah, or the oxygen. Yeah. So mostly the carbon, hydrogen, and sulfur make a reaction with the oxygen, yeah, during the combustion, and also make the next reaction, yeah, for such kind of oxidation, and also the you will have a separate products, yeah, or from the calculation. Yeah, so the product of combustion, you have the heat energy and also work. Yeah, for the diesel engine, for example, you have the, because of the pressure developed inside the combustion chamber, you have the heat energy, high temperature, high pressure, and then you will have the process of work. Yeah, and make a revolution of the crankshaft. But in the boiler, it is a little bit different, because you make an evaporation, you boil the water, and you produce the steam by the reaction of fuel with air in the combustion process. Yeah. So in the exhaust gas products, you will have the excess products. Yeah, not only the heat energy, but also the exhaust gas. Yeah, contains still the basic components like carbon, hydrogen, sulfur, and also an assimilation or new composition of another chemicals. Yeah, because maybe you produce NOx, SOx, and other particulate matters. Yeah. So usually the exhaust gas is not a good matter. Yeah, it means it is undesired matters. Yeah, usually you have, yeah, people doesn't need the exhaust gas. Yeah, so people usually throw away the exhaust gas to the air, yeah, to the ambient atmosphere, but the exhaust gas still contain or bounded the rest energy from the as produced from the combustion. Yeah, so later we will study about the using of the exhaust gas. Yeah, so maybe in the first meeting also I show you about the gas boiler. Yeah, so the waste heat recovery system utilize the exhaust gas or flue gas from the diesel engine or maybe from the gas turbine, and using the exhaust gas to burn or to boil the water inside the boiler. So that's why it's called the gas boiler. Okay, so as I mentioned, that the fuel for the combustion has the calorific value. Yeah, so any kind of fuels has a specific calorific value. Yeah, this is very important. As I mentioned formerly, this is the main value required for the fuel. Yeah, in the combustion process. So you have to first analyze what is the total calorific value, yeah, in 1 cubic meter or 1 kilogram fuel. Yeah. So we can use the basic stoichiometric, yeah, for the calorie value, yeah, the heat bounded in its component. Yeah. So usually a carbon has an energy in 1 kilogram or per kilogram has an energy around 35,000, yeah, or 34,800 kilojoule, yeah, per kilogram. Yeah. And then the hydrogen is more higher than carbon. So it is around more than 100 or maybe around 100,000 kilojoule per kilogram. Yeah. And then you have the sulfur around 10,000 kilojoule per kilogram, nitrogen around 6,000 kilojoule per kilogram, and the oxygen, this is a minus, means that the oxygen is the main part needed for the combustion. So minus here is the energy that will absorb, use it during the combustion process. That's why the energy from the oxygen will be absorbed, use it during the combustion. That's why it is a minus. And then also the water, yeah, because yeah, if the coal, for example, as I mentioned on Thursday, it is naturally that water can be bounded or can be stored inside inside the coal. Yeah, maybe because naturally stored inside, or maybe because of humidity, because of rain, because of humidity and trapped inside the pores. Yeah, in the coals. Yeah. So it will burn and it will evaporate it. Then that's why the value has a minus sign here. Yeah. So we can calculate the net calorific value. So on Thursday, I have explained briefly about the net calorific value and gross calorific value. So the net calorific value, it means that during the combustion process, you use the oxygen reaction with the all components of the fuel, reaction with carbon, hydrogen, sulfur, nitrogen, and then also evaporate the water. So in the net calorific value, the energy from the evaporation, because of high temperature and you make evaporation, you cannot use again the energy from the evaporation steam, yeah, from the fuel. Yeah, it's not the steam from the boiling water in the rising tubes, but it is the bounded water or steam, yeah, produced or developed during the combustion. So you cannot use it again, even from the condensation. So you lost the energy during the combustion or end of the combustion and lose the steam to the atmosphere. Yeah, you cannot get back the energy. But in the gross value, it assumes that you can get back the energy from the evaporation or from the steam by the combustion process and then condense again. Yeah, so you get all the rest of energy, yeah, to boil the water, yeah, and in the combustion or in the exhaust gas, you have the uh, still completely energy, yeah, that you can get, yeah. But in the net calorific value, only the a clean energy from the reaction, chemical reaction of the components with oxygens, yeah. And then you have the heat energy. That is the main production from the combustion, and use it the heat energy to burn or to heating up the water, yeah, inside the rising tubes. So this is the basic formula to calculate the net calorific value. And this is important. In any kind of fuel, you have to know the net calorific value. Usually for analysis, you don't use the gross, but using the net calorific value. Yeah. So you put it the energy for its component and multiplied by the percentage concentration, yeah, in the fuel. Yeah, you can just put it here and minus here, because as explained formerly, this is minus for oxygen and minus for the water. Yeah, and sometimes you can also put the S energy. Yeah, if you know the bounded energy for the S. Yeah. Yeah, this is the formula for net calorific value, and then this is for gross calorific value, yeah, in kilojoule per kilogram. And for gross, this is also the prediction or estimation. Yeah, you can see here that for net calorific, because usually for during the combustion, not all the hydrogen is fully or completely burned reaction with oxygen. And then in the net, usually has a lower energy for the hydrogen. And the gross calorific value, you can use it completely all the bounded energy in the hydrogen, yeah, and use it for the analysis of gross calorific value. Yeah, you can see here that as mentioned, you have to put it minus for water in the net calorific value, because cannot get back the energy from the evaporation of the water in the fuel, yeah, especially in the hard fuels, yeah. But in the liquid fuel or maybe gas fuel, you don't have the water, yeah. So you just skip it, yeah. You cannot delete it, yeah. It is not included in the calculation. But in the gross calorific value, because you get back the energy by the condensation, maybe in the final or the end after the combustion, yeah, after the combustion, then you have the completely energy. So you don't need to reduce or subtract the all reaction or the energy from the combustion with the energy of the water, yeah. But here you still are minus because the oxygen absorbed, yeah, during the combustion. Okay, for liquid fuels, you can use the another formula, yeah, here. So this is based on the function of the density of the liquid fuels, yeah. And usually during the combustion process, as I mentioned formerly, you have a process of reaction, yeah. This is the chemical reactions during the combustion, especially from the carbon, hydrogen, and sulfur with oxygen, yeah. So if you have a carbon react with the oxygen, then you produce CO2, yeah. And then if the hydrogen react with the oxygen, yeah, this is the basic stoichiometric, yeah, you have studied in the senior high school, I believe, and then maybe in the beginning, first or second semester, yeah. So you produce water, yeah, H2O, and then sulfur react with the oxygen, then you produce sulfur dioxide. So please remember this periodic table of the elements. Yeah. So you have the, for example, this one, the hydrogen, helium, and so on. Yeah, many elements here, and usually you remember all the nominal here. Yeah, the value of the mass. Yeah, the mass of the molecules. Yeah, and for example, this the mass, yeah, the mass, yeah, the molecule, yeah, the molecule, the mass of the hydrogen is 1, yeah. You can make it in absolute value is 1, and then the oxygen usually you use 16 for the weight of the molecule or the mass of the molecule, and then for example the carbon is 12, yeah, and for the sulfur is 32, yeah. So I believe you remember these values, yeah. Okay, for example, this from this reaction from carbon, hydrogen, and sulfur with oxygen, because you have the carbon mass is 12, the hydrogen because you the symbol of hydrogen is H2, then you have the total mass is 2, yeah, kilogram per kilomole, and the sulfur is 32, and O2, yeah, because you have a 16 for one molecule, then if you make a chemical reaction with oxygen O2, then you have a 32 kilogram per kmol. So this is the stoichiometric reaction total mass from the reaction between the carbon and oxygen. Then you have around 44 kilogram of CO2. Yeah, you just added the total mass of carbon and oxygen. Yeah, and then for the reaction between the hydrogen and oxygen, you produce water. So from this reaction, you have the mass of water is around 18 kilograms. Okay, so you can also make another reaction with changing the constant here. Yeah? This is the basic stoichiometric. I believe you can also make this kind of analysis, and then you have a 2 molecule of water. Then you have a 2-fold higher the total mass of water. Yeah, and for the reaction between sulfur and oxygen, then you have SO2 here, and then you just added all calculate the total mass. You have a 64, around 64 kilogram of sulfur dioxide. I believe there's no problem. Yeah, you can make also the analysis for such kind of stoichiometric, the basic stoichiometric calculation. Okay, for the next stoichiometric calculation for the combustion, you can analyze also the requirement of oxygen, yeah, for the combustion process. So the minimum requirement of oxygen, you can use this formula in kmol of oxygen per kilogram of fuel. Yeah, so just put it, the percentage contents, the percentage bounded energy for each component in a fuel, put it here. Yeah, for example, carbon you have 90%, for example, just put it here 0.9. Yeah, divided by 12 by the constants here, yeah, using H per 4.032 plus S per 32.606 minus O per 32. Yeah, you just put it all the percentage energy and the reference value at 0 degree of Celsius and 1 bar. Then you have the 32 kilogram per kmol of oxygen, and if you use it the cubic meter, then you have 22.4 cubic meter per kmol. And the next formula is about the air minimum requirement. It should be the, wait a moment. Okay, so this is the air. So usually for the combustion process, you don't use the pure oxygen. You just grab the air from the ambient atmosphere. For example, if you put the diesel engine or the boiler inside of the engine room of the ship, so the required oxygen for the combustion is grabbed from the surrounding air inside the engine room. So you don't need to supply a pure oxygen, for example, from a bottle of oxygen or maybe from a pipeline, a pure oxygen, for example. It's not necessary. So just get it from the air. So in the previous slides, there was the oxygen formula, the required minimum oxygen, but you can also make a calculation based on the minimum air requirement. This is also based on the requirement of combustion. For the boiler combustion process. Or the fuel combustion. The fuel combustion. So in order to have a good combustion process by the mixture, the reaction of the fuel and the air, so you need a minimum supply of air. So maybe you have also started in the diesel engine, and Thursday I also mentioned about the two type of mixture. You have a lean mixture of between the air and fuel, or maybe rich mixture, lean and rich mixture, air and fuel. So you have, maybe you have heard about the air fuel ratio. So you have a certain amount of air for the combustion needed. It's required. You can use this formula. This is also based on the percentage composition of the components in the fuel. This is for the carbon. This is for the hydrogen, sulfur, and oxygen. So you have the minimum air requirement in cubic meter of air per kilogram of fuel. So it means that if you want to burn a 1 kilogram of fuel, at least you need a certain amount of air. Okay. And then for the reference condition, 0 degree of Celsius and 1 bar, you can also make an approximate equation. This is the mass minimum air requirement in kmol per kilogram based on the net caloric value. So the HU here is the net caloric value. So here is the net calorific value. Yeah? You can also use this formula, yeah, for the approximation, yeah, of the minimum air requirement in kmol per kilogram of fuel. Okay? So another analysis or calculation of the combustion, or you can use the Mollier and Boy analysis. Yeah. So the Mollier and Boy analysis based on several constants. Yeah. The fuel characteristic values. Yeah. For oxygen, this is the constants for each component reaction. Yeah. For the combustion process. Yeah. For oxygen, you need a constant here. Sigma. Yeah? Yeah, this is sigma. Yeah. 1 plus 3 per C times the H minus O minus S divided by 8. Yeah. You just make a simple calculation. Just put it the percentage value or energy. Yeah. For example, the C has 90%. The hydrogen, for example, you have 5%, for example. So just put it here. And the characteristic of the hydrogen is omega here. You just use this formula to calculate the constant for the calculation, yeah, based on Mollier and Boy analysis. Yeah. And this is for nitrogen is new. Yeah, this is new. And for sulfur, this is the zeta. Yeah, this is zeta. If I'm not mistaken, yeah, zeta or C. Yeah, this one, the symbol. And for carbon, you can use the constant of kappa. Yeah, kappa. Yeah, yeah. You can use all the formula to define the required constant for the analysis. So then you can use the kappa here. This is a kappa equal 1 plus nu plus zeta plus 3.76 sigma. Yeah. And then you need another constant, it's called phi. Yeah, 0.21 kappa divided by sigma. And you have also another phi, yeah? Another phi with this formula. And K here, sorry, this is not kappa, yeah? This is K. This is 1 for CO2 max. This is the concentration of CO2, yeah? So now you can use the Mollier and Boy analysis based on several constants to calculate the minimum oxygen requirement, yeah, the mass of oxygen required for the combustion. So this is based on the K and sigma, yeah, in kilogram of O2 per kilogram of fuel. Yeah. So K here, yeah, K is based on the this value, yeah, or you can use this value, yeah. And the minimum air requirement, so the above one is the oxygen requirement, and this is the air requirement. Yeah, this is also a function of K and sigma. This is the kilogram air per kilogram fuel. For real practice condition of the combustion, so you need to have a perfect combustion or a complete combustion of fuel. Yeah? But maybe because of the content of components in the fuel, for example, you use a liquid fuels, several deposits, or maybe another parts, another undecided part as fuel, or maybe in the coal you have a water, ash, for example. So you have unburned materials, but it is avoided. This is the undecided materials during the combustion process. So you have to make sure you have to have as good as possible, as perfect as possible of the combustion. So then you have the low unburned material. And the theoretical heat of combustion for the analysis can be used. And one of the main components for the combustion analysis is the air excess ratio. So the air excess ratio, it means the number or the index of the requirement of the air. Lambda, the air excess ratio lambda should be bigger than 1. But a high lambda or excess ratio would result in additional heat losses. And you have to minimize the losses. Then in order to minimize the losses, then you have to minimize the air excess ratio. You have to optimize. So the air excess ratio is the ratio between the mass of air divided by the minimum air requirement. So during the combustion, for example, sometimes the blower or the ventilator of the air during the supply air during the combustion process is more than the air required, more than the required air for the combustion. So then you can calculate the air excess ratio, like this one. So for optimal value of the air excess ratio, so if you use rust firing, it means the coals. Usually the optimal value of the air excess ratio between 1.25 up to 1.35. If you use a dust firing, what is dust? So sometimes the coal fuels is crushed, crushed or maybe pulverized, digerus, seperti menggerus kopi, bagi yang suka membuat roasting kopi sendiri gitu, beli bahan raw-nya, bahan mentahnya yang sudah kopi mentah begitu, atau yang sudah roastingan gitu, nah, kemudian kalian gerus sendiri gitu, ada alatnya. Atau yang suka ngerosting sendiri, bisa aja beli kopi yang mentah, kalian roasting sendiri, kosong, kemudian baru digerus, seperti itu, So crushed or pulverized, then you have in the form of dust, merely a dust size, that's called a dust firing. Later, in the firing system model, we will see the several type of coal firing system. Yeah? So in the dust firing, the optimal value is lower, yeah, 1.20 up to 1.30. Yeah. For the oil firing and gas firing, you have a more lower, yeah, the excess rate. So you don't need excess air. You don't need a lot of air, much air for the combustion process. Yeah. So you need to optimize. Yeah. So the lambda or the air axis can be analyzed or can be predict from the exhaust gas analysis. Yeah. For example, if you use exhaust gas analyzer, I think in our department we have such kind of tools. Yeah. Or Pak Buze, yeah, Pak Buze, I believe he has for the laboratory in the MOM, yeah, such kind of exhaust gas analyzer. So you just inject a probe, yeah, into the exhaust gas port, yeah, so the probe can detect or calculate, measure the exhaust gas parameters and also the components. Yeah. So for example, from the exhaust gas analyzer, based on the CO2 measurement, you can calculate the lambda air excess with this formula. If the analyzing of exhaust gas based on the O2 measured, so you can use this formula for the air excess lambda. Yeah? So you can see here the kappa, the previous constant in the Mollier and Boy. You can use it here. Yeah? Put it in this formula also. Yeah? It's also sigma. Yeah? But if you have both indicator or measurements, then you can also make air excess calculation. Yeah? Yeah. So the O2 and CO2 refers on dry exhaust gas volume, yeah, in cubic meter per cubic meter. Yeah. You can also make another analysis for the exhaust gas for the density, yeah, the exhaust gas. You can also use this common formula to define the density, or you can use the this kind of formula based on the Mollier and Boy constants. Yeah, this is phi omega. Yeah. If you want to change the density, then you can also make adjustment or measurement based on pressure and temperature. Yeah. So 0 here is denotes for the initial condition. For the specific heat of the exhaust gas, yeah, then you can define the specific heat of the exhaust gas based on this formula. Yeah, so you can use the specific heat value from the CO2, from this H2O or water, yeah, from the sulfur, from the air, and also use the constant from Mollier and Boy, the omega, zeta, yeah, sigma, nu, and so on. Yeah, so you just use it all the constant from previous calculation, yeah, from Mollier Boy analysis. Then you can have the specific heat and also the other properties of the exhaust gas or the enthalpy. Yeah. So as yeah, in the heat exchangers, maybe several, maybe last week, yeah. We can also make analysis for the NTU effective methods. Then you know the exhaust gas specific heat or the the steam, yeah, for example. So the enthalpy is the result from the multiplication between the specific heat of the exhaust gas and temperature. Yeah, this is the specific heat at a constant pressure. Yeah. Then you can also make a calculation of the specific of the exhaust gas if you know formally the enthalpy value of the exhaust gas. Yeah, you just put it here, the air access ratio, the specific heat, and also the X. Yeah, this X is the mixture ratio. Yeah, the quality of the exhaust gas. Yeah. And in a wet exhaust, it means if you have a such condition of the exhaust gas that contains the water, the steam, yeah, from the evaporation during the combustion, yeah, then it's called the wet exhaust, yeah. So then you need another formula to define the specific mass of the exhaust gas, yeah. So this is also still based on the constants from Muller and Boy, yeah. Then you can also make a calculation of the specific volume. Then you can also make a calculation of the density of the exhaust gas. This is the formula also based on the constants of the Muller and Boy analysis. You can also make a specific analysis based on the Bunte, yeah, Bunte analysis. This is called the triangle Bunte, yeah, Bunte triangle. So this is the CO2 value. This is the concentration, yeah, specific value of CO2, and this is the mix of O2 and CO2, and you have the diagonal lines here with 45 degree of slope. Yeah, this is in the center diagonal of the rectangular ordinates. Yeah, and then if you know the concentration of CO2 from maybe the measurement using the exhaust gas analyzer, yeah, for instance, then you can put it here, the value of CO2 concentration. For example, you have 15.3%. Just put it the value of CO2 concentration and make a straight lines and cross the diagonal line. Yeah. And then, for instance, if you have the value of the measurement, maybe using the exhaust gas analyzer, you have the concentration of oxygen 21%, then you just put it here, 21, and then just make a straight line and a cross at the a cross section between diagonal, a previous cross section between diagonal and horizontal line of CO2 presentation. Yeah, and then the construction auxiliary line, you can also put it in the Bunte triangle. Yeah, this is for the combustion ratio. For example, in the real combustion process, you need actually 12%. Yeah, so you just put it here. This is for 12%, required, or maybe the produce of the CO2, and make a straight line, straight line, and meet the diagonal lines here, and you have a cross section, the cross lines here, the point between the diagonal and the line of CO2 for the real conversion. And then make a straight line continuous until cross with the line developed by the O2 line and diagonal. So you have the cross point here. So now you can make the combustion ratio. This is first one, and this is the second ratio. So then you can define the combustion ratio of the CO2 and O2. This is the value of the O2 requirement and the CO2 requirement, or the development, the result of the combustion process. So you have 12% and 4% of oxygen, 12% of CO2 and 4% of O2. So based on the if you know the required or the result of the combustion is 4% of oxygen, this is the oxygen from put it from the right lines, and go to the left for 4%. Then you have the remaining gas during combustion. The result of the combustion is CO, or carbon monoxide, 1.2%. So and based on this calculation, you can also make a rough calculation, that the CO itself is around 1.6 contribution or ratio. So the Bunte triangle is quite effective, to analyze the result of the combustion process. So by the triangle of Bunte, you can also make another analysis to find out non-measured exhaust components. And also check the measurement value by the components of CO2, O2, and CO. Okay, so this all the combustion calculation model. So now let's see the example. Or maybe if you have a question, please don't be hesitant. Oke, sudah terlihat ya OneNote-nya. Okay, this is a calorific value calculation. So if you have a coal fuel, if you have a coal with the composition of components, 88% of carbon, 3.5% of hydrogen, 0.8% of sulfur, 2.7% of oxygen, 1.5% of nitrogen, and 3.5% of water. Calculate the gross caloric value and net caloric value. Yeah. Okay, so you can use the formula to calculate the GCV and NCV, yeah? The HO or HU here. Yeah? So for calculation, the gross caloric value based on the modules, yeah, you can use this formula, yeah, this formula. So in the gross caloric value, you have a little bit higher of energy, bonded energy of the hydrogen compared to the bonded energy of hydrogen in the net caloric value. Yeah. Okay. So you can calculate the energy. 34,800 times the carbon, you have 88%. Yeah. And then plus the hydrogen energy times the 0.035. And then times the sulfur reaction energy based on the bonded energy of sulfur times the 0.008. And then plus the nitrogen, the bonded energy of the nitrogen is 0.015. Yeah? And then minus the oxygen. Yeah? Minus the oxygen required for the combustion times the 0.027. Yeah? Then you can calculate the value of the gross calorific value. Yeah? And then for the net calorific value, yeah, you can use the formula from the former slides, from the modules. Yeah? So you can use here 34,800 times the 0.88 times the hydrogen calculation times the 0.025 plus the sulfur times the percentage and then plus the nitrogen, yeah, the percentage 0.015 minus the oxygen required for the combustion 0.027 minus also the uncondensed or losing energy from the water, the steam, yeah? 0.025 minus the 1450 times 0.035. Yeah, you can use this one. Yeah. Okay, so now you can have the result for gross calorific value and net calorific value. Yeah. So the gross calorific value and net calorific value can be used later for the other analysis. Yeah. I think there's no problem. Yeah. I think it's easy. So you can now analyze the value of the calorie yeah, from the fuel. Yeah. For liquid fuel or gas fuel, you can also use the other formula. Yeah. So, but this is the formula for coal. Yeah, for hot fuel. Okay, I think there's no problem. So let's see you can open the seminar talks for STEAM, yeah, the PDF. Start from number 7. The task is for fuel and combustion calculation. Yeah. So for example, in the task number 7, you need to first determine the heat energy which is dissipated with the exhaust gas flow to the environment. Yeah. So it is more or less similar with the internal combustion engine or diesel engine, where the combustion process inside the combustion chamber. So you have lost energy about 30%. Yeah. Lost in the form of heat energy in the exhaust gas and also the heat energy to the jacket cooling water and lubrication oil and so on. Yeah. So yeah, that's why the heat loss is quite high. Yeah. So the first task is to determine the heat loss or the heat energy that is dissipated by the exhaust gas. Yeah. And also the partly exhaust losses by the sensible heat, yeah, regarding to the boiler added energy. So we can analyze the heat loss or the heat energy, yeah, the heat losses that in terms of sensible heat, yeah, by the process of combustion. So the boiler added energy means the fuel combustion process, yeah. So the energy from the fuel combustion, yeah, the burn energy of the fuel combustion process. Yeah. Okay, so we have several known data here. The first one is the fuel mass flow into the furnace, into the combustion chamber. We have 0.05 kilogram per second. And then we have the CO2 content. Yeah, this is the CO2 and O2 content based on the measurement. Yeah, maybe you can use the exhaust gas analyzer. Yeah. So the CO2 content is 12.5%. The O2 content is 1.2%. The exhaust gas temperature 250. You have the ambient temperature 25 degrees Celsius, and you have the ambient pressure a little bit slight sub-atmospheric. Yeah, you have a 98.8 kilopascal. And then you have the specific heat of the exhaust gas, so you don't need to calculate based on the previous formula, yeah, for the specific heat. So you know you have a known data of specific heat of the exhaust gas 1.080 kilojoule per kilogram Kelvin, yeah. And then based on the elementary analysis of the coal, you have the percentage of carbon 87%, 12% of hydrogen, 0.2% of nitrogen, 0.5% of sulfur, and 0.2% of oxygen. Yeah. But you have no data of the S and the water. Yeah. Or just let it yeah as it is. Yeah. So you don't need to think about the required data. Yeah, not the water and S data. So if you have the condition of the dry air in atmospheric pressure and the dry air at 0 degree of Celsius, the density of the air 1.293 kilogram per cubic meter. Yeah. Wait a moment. Okay, so the task, yeah, the first task to define the heat losses, yeah, the heat losses to the exhaust gas, yeah. And the second task is the ratio or the percentage of heat losses from the boiler heat added energy from the combustion, the fuel combustion process. Yeah. So actually like this one, yeah, the heat heat losses divided by the fuel, the energy from fuel combustion, yeah, like this one. Yeah. So the heat losses divided by the Q energy, yeah, from fuel combustion process. Okay. So the first step to calculate the mass flow rate of the exhaust gas. Yeah. Yeah, because the heat losses to the exhaust gas based on the sensible heat, yeah, based on the sensible heat, based on this formula, yeah, the mass flow rate of the exhaust gas multiplied by the specific heat of the exhaust gas and the increasing heat, yeah, the temperature difference, yeah. So the heat losses is the sensible heat that you can calculate, yeah. So the specific heat of exhaust gas, we have the data, the temperature, you have the data, yeah. And then you just need to calculate the mass flow rate of the exhaust gas. Okay. Now you can calculate the mass flow rate of the exhaust gas because the exhaust gas is the result of the combustion. So in the combustion process, you need the air and the fuel So the exhaust gas is the mixing of the chemical reaction between the fuel and the air. Yeah. So the exhaust gas is the accumulation of the mass of the air and mass of the fuel. Yeah. Okay, now you need to calculate first the mass fluid of the air. Yeah. Okay, so based on the previous slides, the previous models, today we know the air excess ratio. The air excess ratio, we can calculate the lambda or excess ratio as the ratio between the mass fluid of the air divided by the mass fluid of the minimum air requirement. Okay. Now we need to calculate the unknown minimum air requirement here. So you can calculate based on the basic calculation to have the mass fluid. This is the volume rate of the minimum air requirement times the density of the air. How to calculate the volume rate? So you have the formula. This is from the former slides in today. This is the minimum volume air requirement in cubic meter air per kilogram of fuel. So like this one. So the volume rate of the air minimum requirement is, so you just to put the concentration of the carbon here, the concentration of hydrogen, sulfur, and oxygen. So you have the composition like this one. You have 87%, 12%, the 0.3%, and 0.5% of sulfur. Okay, just put it here, and then you have the data of the minimum air requirement. You have here, and then now you can calculate the mass fluid. The required mass, minimum requirement of air mass. So you can calculate the value here of the volume air requirement, minimum air requirement times the density of the air. Then you have the mass of minimum air requirement is this data, this value, 14.124 kilogram of air per kilogram of fuel. Times the second. If I because this is the flow rate. This is the flow rate. And then now based on the Muller-Boy, for any constants required for this kind of analysis, now you can calculate the exhaust gas air excess ratio based on the CO2 measure. So let's go back to this model. I hope you can see this slide. For CO2 measurement here, this is lambda. Based on CO2 measure, you can use this formula. Or maybe if you based on both measurement for O2 and CO2, you can also use this formula. Or maybe you just use either CO2 or O2 measurement. You can use this one, or you can use this one. Yeah. Okay, now back to the OneNote. So now you can calculate the R-axis ratio here, yeah, in order to calculate here, yeah, you need the value of lambda here. So you need to define the R-axis ratio, yeah. Yeah. In order to calculate the kappa here, so you need the value of nu here, yeah, this one, and also the zeta, and also the sigma. Sorry. Yeah, the sigma, yeah. The sigma you can calculate based on the Molecular way. You can calculate with this formula, yeah, in the modules. Yeah? You just please check again, open again the slides, yeah, and you have the sigma value here, and then the kappa, yeah, and put it the kappa here, and also the sigma here. Yeah? Okay. Now you have the value of R-axis ratio 1.25. Now, okay, we can calculate the required air, yeah, for the combustion based on the R-axis ratio and the minimum air requirement mass, yeah. Okay, then you have this one for the air, this one, yeah, in kilogram of air per kilogram of fuel second, yeah, this one. Now, sorry for this. Now you can calculate the mass volume of the exhaust gas, yeah, based on the previous formula, yeah, with previous formula here, yeah, this one, yeah. The mass volume of the exhaust gas is the sum of mass volume of the air and the mass volume of the fuel, yeah. Okay. So based on the previous calculation, we have the this one, yeah, this one value, the mass volume of the air, and plus the mass volume of the fuel. The mass volume of the fuel, we have the data here, yeah. This one, yeah. This is the mass volume of the fuel, 0.05 kilogram per second. Now you can have the mass volume of the exhaust gas. And then the next calculation, because you have the mass volume of the exhaust gas already, then you can now calculate the heat loss or the sensible heat loss to the exhaust gas. Yeah. Okay. Just put in the mass volume of the exhaust gas, the specific heat, the known data of specific heat, and the temperature difference between the temperature of the exhaust gas and the ambient temperature, air temperature. Yeah. And then you have around 4,315 kilowatts. Yeah. Okay. You can use the existing data of the specific heat of the exhaust gas. Yeah, here because you have already the exhaust gas specific heat, but you can also make another alternative calculation to determine the specific heat, yeah, of the exhaust gas, yeah, based on the mixture ratio between the fuel and the air, yeah. It means the air content, yeah, specific because the specific heat of the exhaust gas. So you can use the this formula, but anyway, you can use the existing data. By the way, it's also no problem. Yeah, but you can use also the other analysis. Yeah, this is the ratio of the lambda, yeah, the air excess, and between the excess ratio and between the air and the exhaust gas, yeah. So for the air, yeah, this is partial air of the air excess ratio, yeah. So you have the lambda formula, this one, lambda, yeah. Yeah, this is actually 1.2487, yeah. You can put it 1.25. And yeah, for the air like this one, you have you can calculate here. And then for the exhaust gas, yeah, is 1 per lambda. So you have around 0.8. And so the partial air excess ratio between the exhaust gas and air should be 1. Yeah. And wait a moment. So the N index or constant here for air is 0.8, and for the exhaust gas is 0.8, and for air is 0.2, yeah, around 0.2. And then you can you can put it the specific heat mixture in the exhaust gas, mixture between exhaust gas, real exhaust gas, and the air. Yeah, you can put it the existing specific heat here. Yeah, 1.080 and times the 0.8, and this is for the specific heat of the air. You can use the data from properties table, yeah, and then you can have the CP, yeah. Then you can use the more precise condition of the specific heat, yeah, put it in this calculation, yeah. So you can have now the condition of the heat loss, sensible heat loss, yeah, based on the specific heat of mixing between exhaust gas and air. Yeah. Okay. The second task to define the ratio, the percentage of heat loss. Yeah. So the percentage or ratio, yeah, the heat loss ratio between the sensible heat loss and the Q added from the combustion process. Yeah. So the combustion process is the calculation between the mass fluid of the fuel times the net calorific value. So you can calculate the net calorific value, yeah, using the basic formula for calorific value. You have the net calorific value is around 41,564 kilojoule per kilogram. Then you can calculate based on the mass flow of the fuel times the net calorific value. Then you have the fuel combustion energy, or the added energy from combustion process, is around 2078 kilowatts. Yeah. Then you can make the next calculation. Yeah, this is the energy of the sensible heat loss divided by the added energy. Yeah. Then you have the ratio. Yeah, the heat loss ratio. Okay, that's the solution of the task number 7. Yeah, to calculate the determine the heat loss, sensible heat loss, and also the heat loss ratio. Yeah. Okay, I will share. I forgot to put it in the classroom. Later, I will give it to you. Yeah. If you have questions, please. Okay. For the presence check today, wait a moment. Oke, saya cek ya, hadir ya, muka-muka sudah bangun semua ini. Baik, Riz, Kevin, Rifka,
Hadir, Pak.
Faizah,
Hadir, Pak.
Azril, Muhammad Muhibur,
Hadir, Pak.
Wido, Dewi Murti, Michiko,
Hadir, Pak.
Raisa,
Hadir, Pak.
Muhammad Arya,
Hadir, Pak.
Faiza Fika,
Hadir, Pak.
Epifanius, Kristio, Prakoso Putra, Mas Agung, Franciscus Zaverius,
Hadir, Pak.
Daniela, Fakhri, Adifa,
Hadir, Pak.
Maharani, Agung Bintang,
Hadir, Pak.
Akhyar Musafa, Imade Brahma,
Hadir, Pak.
Muhammad Nur Saiful,
Hadir, Pak.
Randy Putra, Mahesa,
Hadir, Pak.
Antonius, Attalarik,
Hadir, Pak.
Gulam,
Hadir.
Tahir, Melvin, Muhammad Zakwan. Oke, ada yang belum dipanggil?
Sorry, sir. I misheard, sir. I'm present, sir.
What is your name?
Kevin, sir.
Kevin. Oke. Any other else? Ada yang belum dipanggil? Baik, that's all for today. Yeah, so it's all. We meet again on Thursday, next Thursday. Oh ya, satu lagi.